When you start a program, most people think execution begins at one obvious place. They think it starts at main, or they think it starts when the first line of code runs. But that's not really what happens. Before your application logic begins, there is a precise sequence of steps that must occur. The operating system creates a process. Memory is prepared. The runtime initializes state. A first thread starts running. The CPU begins executing instructions from a defined address. Those steps are not random. They follow rules. And those rules are what we mean by startup semantics. In this video, we're going to explain startup semantics in a clear, structured way. You'll learn what startup semantics actually mean, how they relate to entry points, what happens during process creation, how runtimes prepare your program before your code executes, what the CPU and operating system are doing during startup, and why startup order matters for performance and architecture. Let's begin with a definition. Startup semantics are the rules that define how a program transitions from not running to running. In other words, startup semantics describe the meaning of start in a computing system. They describe what must be true before the program can execute its logic. They describe the sequence of initialization steps that produce a valid running process. And they describe the guarantees you get at the moment your code begins. Now, why is this important? Because startup is not just a moment, startup is a phase, and many real engineering problems occur during that phase. Slow startup times, crashes before main, configuration loading failures, dependency initialization bugs, threading issues, security problems caused by the environment. All of these are startup semantics problems. Now let's connect startup semantics to something you already know: entry points. In the previous video, we discussed entry points. An entry point is the first instruction executed when a program starts. It's the address the CPU begins executing from. Startup semantics are broader than that. Startup semantics include everything that must happen before that first instruction is executed, and everything that must be true for that first instruction to be meaningful. So think of it like this. The entry point answers, where does execution begin? Startup semantics answer, what does begin actually mean? Now let's walk through startup from the bottom up, step by step. Imagine you run a program in a terminal. Maybe you type a command and hit enter. At that moment, your program is not yet running. You have a file on disk, and you have an operating system that can execute it. Startup begins when the operating system decides to create a new process. A process is a running instance of a program. It has its own memory space, its own resources, and at least one thread of execution. So the first major step of startup semantics is process creation. Process creation is the operating system allocating a brand new execution environment. Now here's an important point. A process is not just a program. A process is a program plus its execution context. That context includes memory mappings, file handles, permissions, environment variables, a working directory, and more. So startup semantics already start shaping the behaviour of your software before your code runs. Next, the operating system loads your executable into memory. This is not just copying the file, this is interpreting the executable format and mapping parts of the program into virtual memory. For example, executable files contain different sections. There's typically a section for machine code, often called the text segment. There's a section for initialized global data, called the data segment. There's a section for uninitialized global data, often called BSS. And then there are metadata sections that help the OS and the loader understand what to do. During startup, the OS loader maps these sections into memory with the correct permissions. Code is mapped as executable. Data is mapped as readable and writable. And this matters, because memory permissions are part of startup semantics. They define what the program is allowed to do. For example, modern systems often enforce that data regions are not executable, which reduces certain classes of attacks. So even security is shaped by startup semantics. Next, the operating system sets up the stack. The stack is a memory region used for function calls, local variables, and control flow. At the moment execution begins, the program must have a valid stack. So startup semantics includes stack initialization. The OS creates a stack region in the process's memory space and sets the stack pointer register to point to it. Now, in many systems, the stack also contains startup data. Things like command line arguments, environment variables, and pointers to other startup information. So when your program starts, it doesn't just magically have args and environment variables. They are placed somewhere in memory by the OS, and the runtime expects them in a specific format. That format is part of startup semantics. It defines what your program can assume about its initial environment. Now we move to the next key concept, the runtime. Many developers think their program is just their code. But in reality, most programs rely on runtime support. Even in C, where people often say no runtime, there is still startup code. There is still initialization before main. That startup code is part of a runtime layer. So during startup, once memory is mapped and the stack is prepared, the OS creates the first thread and sets the CPU's instruction pointer to the entry point address. But remember, in many compiled languages, the entry point is not your main function. It's a lower-level runtime entry, often called _start. So the CPU begins executing runtime startup instructions first. That runtime startup code performs additional initialization. For example, it may prepare the C standard library. It may run initialisers for global objects. It may set up thread local storage. It may perform dynamic linking steps. And only after that does it call main. So when you think about startup semantics, your code is downstream of multiple layers of setup. Now let's talk about dynamic linking, because it's a major part of startup semantics in modern systems. Many programs are not fully self-contained. They depend on shared libraries. On Linux, these are shared objects. On Windows, DLLs. On macOS, dynamic libraries. If your program uses shared libraries, the loader must resolve those dependencies during startup. It must locate the libraries, map them into memory, resolve symbols, and in some cases, perform relocation so addresses point to the right places. This is a huge part of startup time for many applications. So if you've ever wondered why a program takes time to start, even before doing anything, dynamic linking is often a major reason. And again, this is startup semantics. It's part of the rules that define how start happens. Now let's talk about one of the most important and most misunderstood parts of startup semantics: global initialization. In many languages, there is code that runs before your main function. In C++, for example, global objects can have constructors. Those constructors run before main. In many runtimes, there are static initializers. In Java, classes can have static blocks. Those can run when the class is loaded. In C#, static constructors can run before the type is used. In Python, top-level module code runs when the module is imported. So startup semantics include rules like: when do global initializers run? In what order do they run? What happens if initialization fails? What guarantees exist about readiness? These rules matter because they influence architecture, they influence testability, they influence failure modes, and they influence performance. Now, let's connect startup semantics to threads. Every process begins with one thread, the main thread. Startup semantics define what the main thread runs first. In a simple program, the main thread starts at the runtime entry, then calls main, then runs your code. But in many systems, threads can also be created during startup. For example, a managed runtime might start a garbage collector thread. A web server framework might start background threads early. A GUI framework might start an event loop and delegate tasks. So startup semantics include the rules governing what threads exist at startup and what they're allowed to do. And this leads to a major architectural insight. The way your software starts often determines how your software behaves under load. Because the initialization phase establishes caches, dependency graphs, configuration, logging, security policies, and concurrency models. Startup is the foundation. Now let's compare startup semantics across two broad categories: compiled programs and managed runtimes. In a compiled native program like C or C++, the OS loads the binary, maps memory, resolves dependencies, sets up the stack, starts the main thread, and jumps to the entry point. Then the runtime startup code runs, initializes the environment, and calls main. After main returns, the runtime performs cleanup and exits. In a managed runtime program, like Java or C#, the operating system starts the runtime first, so your program is actually loaded and executed by another program. In Java, the OS starts the JVM. The JVM performs its own initialization, memory management, JIT compilation infrastructure, class loading, verification, and more. Then it loads your application and searches for your main method. Then it calls it. So the startup semantics of your application include both the operating system startup semantics and the runtime's internal startup semantics. That's why startup can be much slower in managed environments, because there's more work to do before your code runs, but it also provides more guarantees. For example, the runtime may guarantee memory safety properties, sandboxing, or predictable lifecycle hooks. So the semantics are different. Now let's connect this to a practical point. If you're designing software, you should treat startup as a first-class part of the system, not an afterthought. Because startup is where configuration is loaded. It's where dependencies are wired. It's where secrets might be read. It's where environment variables are interpreted. It's where connection pools might be created. It's where logging is configured. And if startup is messy, your system becomes hard to reason about. Now we should address a subtle but important concept. What is the boundary between startup and runtime? In simple terms, startup is the phase where the program is moving from not running to ready to perform its purpose. Runtime is the phase where the program is doing its intended work, but that boundary can vary depending on the program type. For a CLI tool, startup ends quickly and runtime is the main computation. For a web server, startup ends when the server is listening on a port and ready to accept requests. For a GUI application, startup ends when the event loop is running and the interface is responsive. So startup semantics are not just OS level and CPU level. They also exist at the application level. A web server framework might define lifecycle hooks like initialize, start, and ready. Those are higher-level startup semantics layered on top of the lower-level ones. Now let's discuss why startup semantics matter for performance. A common performance issue is slow startup. If startup is slow, the software feels sluggish to users. It increases cold start latency in serverless systems. It makes deployments slower. It affects auto-scaling, and it increases time to recovery after failure. Many systems today are evaluated not just by throughput, but by startup behaviour. So understanding startup semantics helps you optimize. For example, you can reduce dynamic linking overhead. You can minimize global initializers. You can defer heavy work until after readiness. You can reduce class path scanning in managed environments. You can pre-compile or cache runtime components. All of these are startup semantics decisions. Now let's talk about failure modes, because startup failures are uniquely painful. When a program fails during startup, you often get limited information. Logging might not be configured yet. Dependencies might not be initialized yet. The system might crash before producing meaningful output. So robust systems treat startup as a controlled sequence with clear error handling. They validate configuration early. They fail fast when critical requirements are missing. They expose readiness and health signals. And they keep startup deterministic. Determinism is key, because the more non-deterministic startup becomes, the harder your system is to debug and reproduce. Now let's clear up a few misconceptions. Misconception 1. Startup is just loading the program. Startup includes process creation, memory mapping, dependency resolution, runtime initialization, and application lifecycle steps. Misconception 2. Entry point and startup are the same. The entry point is the first instruction. Startup semantics include what must be true for that instruction to be meaningful and what sequence leads from start to ready. Misconception 3. Startup happens only once, so it doesn't matter. In modern systems, startup happens constantly. Containers are started and stopped. Functions, cold start. Servers autoscale. Mobile apps are opened and closed. Startup performance and correctness matter a lot. Misconception 4. Startup is deterministic by default, not necessarily. Static initialization order, dependency injection order, environment differences, and race conditions can introduce unpredictability unless you design for determinism. Now let's summarize. Startup semantics are the rules that define how software begins executing. They include process creation by the operating system, executable loading and memory mapping, stack and environment setup, dynamic linking and dependency resolution, runtime initialization before main, global and static initializers, main thread startup and early thread creation, and higher-level application lifecycle readiness. Startup is not just a moment where a program begins. Startup is an execution phase governed by rules, and understanding those rules gives you deeper insight into how software actually runs, from CPU instructions to processes to runtime behavior to architecture. In the next part of this execution series, we can go one layer deeper and explain how the CPU executes instructions step by step, and how the instruction pointer drives everything that happens inside a running program. And if you want a clearer mental model of concurrency, we can follow that with processes versus threads, and how software creates and manages threads at runtime. For now, if you've been thinking of startup as main begins, you can replace that model with something more accurate. Startup is the controlled transformation from a file on disk into a running process with a valid execution environment. And that transformation is defined by startup semantics.